Okay, so today what we are going to do is we are not going to take up any new topics. We are just going to revisit some of the important topics which is essential for your T2 exam, right? Okay, so this was not there in your first semester, although in the first test, so this might be included in this test. This is NAND implementation. If a K map is given, you need to make an NAND implementation from the K map. Okay, so are we clear about how to make this NAND gates, right? It is actually an AND OR combination. If it is a simple AND OR combination, you can just replace it with NAND, that will work fine. Otherwise, you now need to put those bubbles and move forward. So anybody has got any doubt on how to get this circuit from here? Anybody has got a doubt? Right? It was this K map, though everyone knows, right? Okay, on what changes, a quick review on what changes what's okay. So this is the K map we made. So for this is an expression here and 8. So this is going to be what is this? This is A, right? This big one is A, and these two are going to be B dash C D. Right now we are assuming that B dash is not available. So you have put a NOT gate here, you have put a AND gate and a OR gate out here, right? So yeah, I'll upload these slides also. Don't worry, you don't have to note down anything. Even the video I will upload, no problem. So we are going to put an OR gate out here, right? Once we put an OR gate here, now we need to convert this as a NAND. So we are going to put a bubble here. So we put a bubble here, right? This NOT is just we have shorted the input, so this NOT. Now we have put a bubble here. Now for this OR to become an NAND, we have to put one in the input side also. So input side also we have put a bubble, but this bubble and this bubble will get cancelled, whereas here it is A and there is no bubble to be cancelled. There is no corresponding bubble available. So here it will have become NAND. So this, to cancel this bubble which has converted this OR into NAND, we have put one more inverter here. So we have used an NAND 2. So this is how we get this circuit. Anybody has got any doubts with this? Then we can move on to the next step. So if such circuit is given, I guess you will be able to easily make this circuit. Is it okay with all of you? Can somebody say yes or no? Then I can move forward. Okay.
Yes, sir.
Okay, good. Right. Okay. This is NOR implementation. In case we are grouping zeros, right, for an expression, we will get like this, right? That K map is not shown. From the zeros if we do it, OR AND application, right, from the max term we'll get, this is the initial type of gate which we will get. So we are going to put an to make it NOR, 2 bubbles here. So we are going to put 2 bubbles here. So this is AND gate. So this, obviously if you put one more bubble only, then this will become NOR, but this bubble doesn't have an gate to cancel. So this E has become E bar here, right? So we have put an E bar here, right? In the next stage what we have done is, okay, we have replaced this all input inverted AND to a NOR gate, and this E bar we have again reverted back to E and put an NOR gate here. Okay, this single line indicates the 2 input lines are shorted with each other. Is it okay? Anybody has got a doubt with this kind of simplification? Okay. Okay. So now coming to the next. Okay, this is pretty important. 5 variable maps. You have to be very careful with what you are doing in exam, right? So the technique is, if it is a 5 variable, you take one as outside, right? One of the P is equal to 0, and for P equal to 1. Here the MSB has been taken out, right? In the MSB you have taken out, and QRST we had made different these things. First we make the individually we are going to make the K maps, right? So these 4 K maps. Now after having made it individually, okay, we have to see whether this is group, it is available here also, right? That means it is not dependent on P. So this long one is actually S dash T, right? So we write S dash T because it is common to both of that. We don't take P into consideration. Okay, the next one in this is these four corner ones, right? These four corner ones are also common here also, these four common ones, so we don't take that into consideration, and that four corner ones is probably R dash T, so we write like that. Okay, and if you see these two ones, again these are common to both the things, so there also we don't take into consideration because it is independent of P, so we don't take into consideration, so that we get as Q dash RST, right? And the final one, this yellow which is put here, this is not available here, it is only available for P equal to 1, whereas this expression for this is QR dash, so we put a P there. Is this clear, Shreya? Anybody? Yeah, okay. So expect something, similar questions will be there in your exam. Okay, and this is gray code method. Okay, this is also equally important. In the gray code method, okay, we take a single table and this will continue like a gray code here. So in this case, these two can be clubbed as an single box. Also you will find these four and these four also be clubbed because it's an vertical mirror. Along the vertical axis, this is flipped here like a mirror here, so these also can be clubbed, these four, and these two and these two are also clubbed here. Are you able to see my mouse? I just forgot to make it slightly bigger. Are you able to see?
Yes,
my you are able to see? Okay, so so we know now how to make, and these two corners also can be clubbed. So in case of an problem is given in a gray code, you should know how to club these things. So so I don't make the questions too complicated, just that you should know the technique. That is good enough for me. Is it okay for all of you if some question is asked like this? And is there any doubt? You can ask me now. Yeah, it's okay, then we move forward. Okay, so yeah, even this is also important. Once if you don't know, anybody has got a doubt on how to make these tables here, right? Okay, so don't get surprised if you find that if this 0 1 is written after this 0 0 0, right? It is pretty, still it is very clear, right? Doesn't matter, because obviously when you are writing 0 1 2 3 4 here, it means min term. I am telling you right now itself. There are some questions like this in which these min terms are written on the right hand side. Okay, all these min terms, after this it is written on the right hand term. So don't ask me questions and doubts on that. Okay, these will be written on the right hand side. Okay, first these will be written and then the min terms. It means all the same, right? Just you have to, obviously this cannot be binary. So here also, if it is written 14 here, that doesn't mean binary. So the min terms, even if it is written to the right hand side, okay, so it means the same thing. So it is pretty simple. Like if we this is the grouping, right? Number of zeros are 1, number of zeros are, right? Here the number of ones are 0, the number of ones here is 1, number of ones here is 2, number of ones is 3 here from the min terms. Okay, we group the min terms accordingly here in the first step. In the second step, what do we do? Okay, we compare each this 0 with 1, 2 and 8. Okay, we are going to compare it, and if there is only one change, we put a dash here. So these kind of problems might be there. Yeah, anybody has got a doubt on how to make these tables and interpret it, and in fact you got to write these expressions 1 2 3 4 5 6. In this case, these 6 expressions are there. So there could be some question where these tables will be there, and we might have to make these 6 expressions. If there is no group 1, we should see group. Yeah, there could be a possibility there is no group 1, that could be there, right? That will be there, and that is there. So from these tables, you know how to write the expressions. This should be clear to you. Okay. It's going to be 30 minutes. Okay. So
Sir, excuse me, sir.
Yeah, tell me.
So in the case there is no group 1, then there cannot be 0 2 pairs, right? Group 0 and group 2 cannot be paired. So like
Yeah,
that will be the last column.
Correct.
Okay.
Then you'll have to.
Thank you.
Yeah. Sai Krishna, could you explain how expressions are written once? Yeah. See, this expression is like 0 0, right? So it is wx yz. So it is x dash y dash. This is a 4 variable. I didn't put that first part of the question here. It is taken from the class slides only. So this is an x dash y dash. Okay. Similarly, you have to see that, and if there is something left out here, don't miss out these terms in the exam, right? Okay. So okay. So okay. So you have to be careful. This is the mistake generally we do. We leave out, we just concentrate on the last column. So if anything which remains unticked here, you need to be careful with that. So that is the mistake generally you guys do. So be careful with that. Okay. Then yeah, there could be some questions based on optimization, finding essential prime implements from the prime implicants, right? So there may not be a question which is both this and that. So I'll split into 2 different questions, so that time consumed is not that much. So so from here, essentially you'll have to first tick out those elements which are essential. Like if you have some elements which is there only in that expression, like here here what you have, this element, right? So this expression has to be there because this minterm is reflected only in this expression. So you have to first select those kind of elements, and then subsequently you have to find out the minimum possible combination. So in the class it is well explained. So just revise this portion also, right? So as soon as this class is over, I will upload this PDF, so you will know what are the topics which are important. So these things you have to see. This expression is covered only by this minterm. So this is not the final answer, right? Prime, essential prime doesn't mean only this and this. Okay, when I ask a question on this, don't write just these 2 expressions. Okay, these 2 expressions plus what are the other expressions also you need to write, right? These 2 in this case, is it covering all the expressions? You have to see, right? So that way. Then glitch we understand, right? If there are 2 ones which are not covered, see, only this expression is good enough with for an basic implementation, which is shown in red. But if you want a glitch free circuit, then you might have to take 1 also. So so these kind of questions are also there. Okay. Yeah. This is multiple output circuit optimization. So I told you we have to essentially first you take each of these functions and find out what is the element which is not common here. So if we find this is the one which is not common to these 2, then we make the biggest possible function out here. Okay, so we make the biggest possible function here. Similarly, this is not available here and there, so we make the biggest possible grouping here after having, but here all these are either reflected here or here, and then we make the we take each of them and try to find out what is common and accordingly group. So this PPT is also available with you. Okay, then I missed out something which I wanted to tell you. Okay, let me just not here. Yeah, when you make an expression like this, right, this is for the zeros example. For the one, suppose we make the expression like this. Okay, there could be a possibility that you can club these two terms also, right, and simplify it. So the answer, so after getting this, if you find the answer is not matching exactly with the choices, okay, just see there could be some more optimization which is done there. So if you look at the answer carefully, then you will find that what you want and what is available there is still there, right? There is some optimization which has been done between two terms. So you have to be, so accordingly I have given more time for that question and more marks, so you have to be careful with that. Okay, so if you don't find the answer exactly, okay, after from the K map, okay, if you are not finding the answer, then you have to spend say 30 seconds more and try to find out what is the equivalent which is given in the answer. Is it okay with all of you? Understood what I want to say? Can somebody say yes or no? Yeah, right. So if you are, when I'm telling it in very clear terms, okay, I'm giving a big hint that once you find this answer for a 5K variable, exact same answer may not be there in the choice. You might have to do one level of optimization further to find your answer in the input. Okay. This we said, these kind of questions will be there. These also might be there. Full adder, this we saw, right? This is normal full adder, right? How to implement it. So if you see in this particular full adder, the carry out delay is 2 gate delays, right? Sum is also delay and carry out is also 2 delay. So this is a ripple carry adder. We saw that with each stage the delay will keep increasing as you keep moving out here, right? So we saw 4 into full adder delay, the total delay out here, right? Then we saw
Sir, excuse me, sir.
Yeah.
Sir, can you explain how the sum has a two gate delay?
This is
In the
this is 1 gate delay, right? And this is the second gate delay. So say A and B are changing, worst case scenario. So first the change has to be reflected here, and then the change gets reflected here, right? And this here also there are 3 AND gates, so it would get delayed out here once, and that again one more gate delay here, right? So this has got 2 gate delay. Whereas if you make with the full adder with 2 half adders, then the carry out delay is 3 gate delay. In this particular configuration, it is 2 gate delay. Is it okay?
Yes, sir.
Yeah. Probably in the class, Ria, when I was talking, I think I was talking about the 2 half adder delays, and there probably we assumed the cout is going to be 3 gate delay. I didn't put that circuit in between. So if you use 2 half adder delays, then it will be 3 gate delay. You want me to flash that slide? How that 3 gate delay came? Okay, I can do that. Let me just see. This was half adder. Yeah, if I am talking about this implementation, this full adder implementation, it has got a lesser number of gates, if you see, than the previous one what we discussed, but lesser number of gates, but it has got 3 gate delays, because if you see it is coming here 1 gate delay, second gate delay, and 3 gate delay. So this particular half adder which we made using 2 half adders has got an lesser hardware. It has got total only 5 gates, but the carry delay is 3, right? Whereas here if you see, the number of gates has gone up, 1 2 3 4 5 6. The number of gates are higher, but the carry out has got 2 gate delays. So in case there is a question in this regard, it will be specified in the question, so there will be no ambiguity, right? Okay, so this is, that's why I have not specified here whether it is 2 gate delay or 3 gate delay. I have written 4 into full adder delay for a normal ripple carry adder, right? For a carry look ahead adder, okay, so the question it will be like there is an carry will be generated, propagation will be generated, and the generate will be. So these are the circuit which we use in a carry look adder block. So this will be the expression for that, and if you see the big block, then the total delay is just the 3 gate delays, right? 3 gate delays, 2 gate delays here, and the third gate delay to from here to generate the propagation and the so the total gate delay out here will be only 3 gate delay, constant 3 gate delay, right? For this configuration it will be like that. So multiplier, so this you can just revise it. I will not put any question from here because it's too lengthy, but definitely in the compre there might be some questions of this, some variations of this circuit in the compre. I have framed that, but I have not put that here. Okay, yeah, these kind of questions are also important. Decoder based, right? If you have access, if you have to implement a function, basically implementing a function, 3 to 8 decoder, right? So how to implement a function? Yeah, most likely we don't know, like the AGS RD is working out on, by November they said they will find out a solution how to do compre. Maybe they'll have test centers at various places. I don't know what they're going to do, so that will be a totally different. So based on what they say, what is the scheme they are going to implement, so in that case accordingly I will not I'll mostly keep it multiple choice only. I guess I'll give more time for each question. It will be like in GATE you are writing all multiple choice questions only, right? But there will be some hand calculations required, because for 600 students evaluation will become difficult, and if I delegate the evaluation to different instructors, each one will do with his own yardsticks. Somebody will get an higher mark, lower mark, so all these confusions. So let's see, I'll stick to multiple choice questions, but the questions will obviously will require some hand calculation, so I'll do that, right? Okay, so these type of questions also will be there. This is pretty easy. So these are all free gifts, marks, like so that at least nobody fails. At least you will get the minimum mark required. There will be some tough questions where, okay, this is binary to gray encoder. This we saw from a decoder. Okay, I just wanted to flash this slide because I made some, these connections are fine, but in the earlier PDF which I had uploaded, I had made even in the classroom I had made some random connections here also. That random connection I just wanted to tell you, okay, by making random, whatever function we want we can change, okay, but they were not correct actually. Okay, so I just these were correct. So anybody has got a doubt on how to use this encoder decoder function to make different functions, to transform a function? Is it clear to all of you? It's a doubt class. If you have any doubts, I can explain it. Yeah. Okay, let me move forward. Yeah, these are again important multiplier based design, right? Okay, so it is both ways. You have to understand that it is like if this function is given, you make an mux design. You should also try, and if a mux design is given, you have to make a function also, right? So be careful with that. So it could be either way. The question could be that there could be a function and you make a mux out of it, or it could be the other way around. A mux is given, you have to identify what is the function, right? So you need to write the expressions and try to get an answer for that. So those kind of questions also you can expect. Yeah, these functioning of the latch has to be extremely it's important, right? So there will be some hand-drawn graphs also, so you'll have to know, like it is set is, when set means it is setting it to 1 output, reset means it is resetting it to 0, right? And there were few students who asked me doubt on D flip-flop, like here, right? So if you see in these people, few students had a doubt. See, reset and set, it overrides the clock and data, right? During that time, it doesn't wait for a clock signal. The moment set or reset, the output would toggle. This set and reset is the highest priority one, which will straight away do the reset and set in the output. It will not wait for the clock. Is it okay with everybody? Anybody has a doubt? Otherwise, if you can say yes or no, it will be easy for me to move forward. Yeah, okay. See, this set and reset signals, right, are not clock dependent. The moment, like in this case, if you see, the moment the set has gone down, clock has not yet come, but the output has straight away gone to high. It is set bar. Set bar means the signal, if it goes low, output has to go high. This is set bar. This is reset bar. Similarly, the reset is going down here. Okay, in this case, this is directly moving here, right? So it is as per the clock, doesn't matter. But if you see the set signal here, right, the set signal is going low here, so the output is straight away coming to high. It is set bar, so it has to go high. It is not waiting for the clock, right? Here also you can see the same thing which is happening. Is it clear to all of you? The set signals and reset signals are not dependent on clock, right? Whenever they go low, immediately the output will be set to 0 or high. The clock need not be high. So that is the important thing which you got to remember.
Excuse me, sir.
Yeah, tell me.
Sir, even if the clock is changing at that time, if set or reset is 1, then it will be overridden, sir.
Yeah. You can say when the set and reset is there, all other signals are disabled.
Okay, sir.
Right? After that, it goes, then it will hold on to that value, whatever is the value. When the set again is going here, it is going 1 because it is set bar. Then till the next clock edge, it will remain the same. Is it okay?
Yes, sir. Thanks.
Venkat, is it clear? Kedarnath? Yeah, okay. Shreya, it's okay? Yeah, okay. So got to be careful with that. Okay. Other flip-flops, yeah. Even JK flip-flop is an important one. You have to be very clear with these characteristics. 0 0 means it is no change. 0 1 it is going to be reset to 0. 1 0 it is going to be set to 1, and 1 1 it is going to toggle. This has to be very clear. You will have some question based on this. And during the positive edge trigger, if you see, so this waveform, how do we get this waveform? You have to be clear, right? Let me just, okay, here. So if it is here, when the clock is going high, J is 0, k is 0, so it remains 0, and then it will remain 0 till the next clock. In this clock it is 0 0, again it will continue to be 0 here, right? And this positive clock you will find it is 1 0, so it is set to 1 here, and this clock it is 1 1, so it is toggle means 1 will become 0, so it will become 0. So be careful with these kind of graphs also, right? So T flip-flop, we know if it is 0 it will just toggle, T is equal to 0. So if it is 1 it will toggle, whatever, if it is 0 it will toggle to 1, if it is 1 it is going to toggle to 0. Here it is a positive, T is 1, so output has toggled here. Again it is going here, T is 1, it is toggle. In the next clock it is 0 here, so it continues to remain 0 here, it will not toggle. So these kind of graphs are also important. So I think I have covered a few important topics. If you have any doubts in any specific topics, you can ask me now.
Sir, can you explain the enabling application, like the function, like how do we actually implement enabling in the circuit?
Enable, okay.
Yeah, enable bit.
Yeah, okay. So there's sequential circuit design is not part of this one. Okay, this circuit, to answer Shriya's question. Enable is probably we had that.
Yeah, that was in the decoder and multiplexer thing.
Right. In the flip flops also, I think I had flashed few circuit. Let me just see. Here you have this enable pin, right? On the D flip flop. If this is 0,
Yes, sir.
D will not go further ahead. This will block here. Okay.
Okay.
This is S dash R dash latch. So if enable is 0, it will be 1 1 here, right? So it will maintain the previous state.
So, like, if you want to implement it on a like let's say LT spice, then we'll give it as the most significant bit. Like the frequency will be the highest. So, like, it will be enabled for most of the steps and then not for the other steps, right? Like, if my circuit requires 0.16 mu for the normal application, then enable will be for 32. Like for the first 16 times it will be closed and then other time it will be open, right?
No, enable will be a different pin altogether. If you want to keep it continuously high, right?
Okay.
Enable, you can just give 5 volt supply there or a 0 volt supply there.
Okay, sir. Yes, sir. Okay, got it, sir.
Right? Okay. Now, like I said in the previous case also, see, if you see this preset and clear is given here, right? So if I put preset bar, right? So irrespective of what is coming from the clock or D, this will be if you give a 0 here, it will become 1 here, right? So it will become preset to 1. Similarly, clear means 0. If you give an clear bar, it is. If you give 0 here, irrespective of the clock or D input, it will be set to 1. That is why that in that graph we saw somewhere it is known as preset and clear, or it will be in some ICs, some manufacturers prefer it calling it as reset and set, right? Reset is clear and preset is set. So you see this input is directly given at these NAND gates at the output. So it has nothing to do with the clock and also it has got an highest priority here. So you can also see that from here also. Is it okay? Okay. Is there any other doubts? Okay. If there is no doubts, we'll stop it here and